right? And this gets me now to our last why this matters, right? Do I need a moment? And I'm doing it on the backdrop of this beautiful periodic table, right? So that's a lot of energy, by the way. You know, first you had to make these iron pipes, and now you gotta case harden them, right? Or maybe you gotta put even more iron in. Look at the oven, 900 C is really hot. How much energy do we take to make stuff as simple as concrete, right? Doesn't it it's just liquid stone? Didn't you just grind some stones down or something and then pour it out, right? Actually, if you think about concrete and other materials like steel, right? The use of them is skyrocketing, right? This is how much we're making, okay? So so look at this, the millions of tons. There's steel and there's cement. Look at that. There's the world population right there, and this runs out in 2010, 11, but it's continuing. It's continuing because it's not just that the population is growing, it's that the places that the population is growing the most are also industrializing. And that means building. You go to some of these places and there's a new building literally every block. There's a new building being built. That takes this stuff. That takes a lot of ovens and a lot of really high temperatures. Just the cement alone is accounting for 7% of all CO2 emissions. All CO2 emissions on the planet, 7% of that goes into simply making this magic liquid stone, this powder. And at the core of it, what is at the core of it? It's chemistry. It's clinker. It's called a clinker. What is a clinker? It's this thing. It's simply a calcium silicate group. Making that is what takes all this energy. It takes half of it at least, making that right. And it's as always, the chemistry gives us the chance to get out of our constrained optimization. Right? And so you got to make this mixture of different types of synthetic rock. You got to make mixtures of alite and belite. They have different names. And you might be able to make more belite, which takes less energy. You can cool your oven down by 300 C to make belite compared to alite. Yeah, but then, even though it's structurally okay, it takes 90 days to dry. So you can't do that. So you got to spend the 300 extra Celsius to make more alite. Why? It's in the chemistry, right? It's in the chemistry. And understanding what seems like not a very interesting, cement, is it really that interesting? You bet it is. 7% of all CO2 emissions is just making this one material. And we're making a lot of it. We're making a lot of it. There's a tower, 160-floor tower in Dubai that opened in 2010 that took 1 billion kilograms of this stuff, right? So now, this makes a lot of CO2. And I've talked about CO2 throughout the semester, right? And so one thing I wanted to leave you with was also some things that we're doing about it. What do we do about CO2? So how is carbon capture and sequestration going, right? Could we take it all out? We put it in, could we take it out? And so I'll share a couple of things. So, one of the problems with CO2 capture is that if you don't do it right where you make it, then you have to transport it. And it turns out that's actually it's really hard to transport CO2. And there's a lot of problems that have happened over the years. In the 80s, there was a leak that killed thousands of people. There have been massive leaks in Canada in transporting this material. So transporting is actually really hard to do. There's metal pipe corrosion. This is a great chemistry problem, unsolved. And then the next part of CO2 sequestration is, so one is transporting it that's challenging, and the other is storing it. What do you do with it? Let's suppose we could capture it. Well, then what? And there's ideas around this, right? So you could pump it maybe underground, geosequestration. I mean, that's not a sure thing. We don't know, we don't understand at those scales exactly how well we can encase this material and how long it will last. There's a lot of questions with that. There's a whole line of thinking on putting it in the ocean. Right? Really? So you want to fix the CO2 problem by acidifying the oceans even faster? Okay, interesting, right? So transport and sequestration is a big problem. But what about technologies where you simply sequester it right there, where you make it, like clean coal? Right? You may have heard of clean coal, right? So clean coal. So I'm going to look at a case study of a clean coal project in the U.S. In 2005, I got really excited because 8 companies joined, and it was called FutureGen, and the U.S. government was going to put a lot of money into it. They were going to capture 90% of the CO2. You get a little bit less efficiency, depending on how you think about it. It could be 30% less efficiency, less power out of the plant, but you sequester the CO2. And in 2009, construction was planned in Illinois. In 2010, it was canceled. In 2010, it was restarted. In 2012, there was all sorts of discussions with the DOE that agreed to pay $1.1 billion. It was all located, and then the companies dropped out, and the DOE canceled the project. So that was 10 years. 10 years, and $200 million of taxpayer dollars, and absolutely nothing has come out of it. So one of the things I want to point out about this direction, and I'm not saying that it's not a good direction to keep pursuing, but the timescales are long. And so we need to be able to make decisions that can cover longer timescales. That's a huge part of the challenge with this. It's a policy challenge as much as it is a technical one. There is, and tying this back to the cement, there is some really interesting research that's going on in actually, instead of, okay, so you got the CO2, it comes out when you make it because the ovens and you're burning stuff, but what if you could take that CO2 and just put it into the thing you're making? And by the way, if what you're making is a huge scale like cement, then maybe you could put a lot of it in, right? And maybe that could have a real global impact. So there's a lot of interest in substantial global carbon uptake by cement carbonation. So maybe you could get some of it in the cement. I like this paper. I'm pointing it out because they say that they use fixed diffusion law. They modeled the carbon uptake by applying fixed diffusion law. Yeah, it actually matters. Right? You can do this too now. And just a few weeks ago on CNN, there was this concrete, yes, concrete is going high tech. Why? Because this company has managed to figure out how to put a bunch of CO2 into the concrete while they make it, and it doesn't change the mechanical integrity of the concrete. And it's in there. It's actually in there, right? This is all chemistry. This is all chemistry. So this is, I think, another very interesting direction where technology can play a vital role in this particular global challenge. Okay.